A very warm good morning to one and all. Myself, Dr. G. Haripriya, convener, head of the Department of Humanities and Basic Sciences, professor in Mathematics, Gates Institute of Technology, welcome you all for day 4 of a one-week faculty development program on advanced materials, processing and characterization methods. Let's begin our session by introducing our honorable resource person, Dr.Pandiyarajan Tangaraj sir, who is highly knowledgeable and dedicated professor in physics. Sir has completed PhD in physics from National Institute of Technology, Trichy, Tamil Nadu, on the title Doping and Polymer Covering Induced Optical Vibrational Properties of Zinc Oxide. Master's degree in physics from NIT, Trichy, Tamil Nadu in the year 2009. Bachelor's degree in physics from the American College, Madurai in the year 2007. Coming to professional experience, Dr. Pandiyarajan is a highly experienced and respected physics professor with over 2 years and of rich teaching and research experience. Currently, Sir is tenured Assistant Professor of Physics at IIIT Design and Manufacturing Kurnool, where Sir teaches undergraduates and master students in digital electronics, principles and applications, nuclear science and engineering, physics of nanostructured materials and nanoscale devices, and many more. In addition, Sir's rigorous academic research experience as postdoctoral research fellow in institution and visiting research in various countries like Sweden, Mexico, and South America. Sir has received many honors like organizing member of International Conference, steering committee member of Young Professional Network USA, also served as secretary of NITT-SPIE student chapter in the year 2011 to 2012. Sir has ultimate skills in synthesis of nanostructured materials and fabrication of thin films. Sir has completed many innovative projects. Presently, ongoing project is development of graphene quantum and design of pilot scale. He has published international and national journals and authorized books, organized FTBs, conferences and symposiums, has membership in scientific society. We are very fortunate to have you for this session, sir. I request sir to take over the session. Thank you, sir. Welcome, sir.
Thank you, madam. Thank you. First of all, I thank Gates Institute of Technology Management and HOD Humanities and Sciences, Dr. Haripriya ma'am, for inviting me to give lecture on nanostructured materials in this FTB or 1 week faculty development program. I thank you, madam. So let me share the screen. Just have a look. Is my screen is visible, madam?
Okay, sir. Visible, sir.
Okay. Full screen mode is there, no? Right?
Moving, sir.
Okay. Let me start. So actually today I'm planning to give the talk on advanced nanostructured materials for environmental applications. So specifically, I'm going to take 2 different applications. One is related to wastewater, and the other one is related to human body, which we are day-to-day life, which we are using as a sunscreen applications. Okay. So the outline of talk is going to be something like this. I'm going to I'm going to separate my talk into 6 categories. First, I will just give what is the need of wastewater treatment, why we need to worry about wastewater treatment in the present context. And then secondly, I will talk about various technologies involved in wastewater treatment, traditionally as well as the present context, like in the advanced level and the currently what people are using for wastewater treatment. Then the material which we are going to use as a title, as I said, nanomaterials. So I'm going to use, I'm going to give the glimpse of photocatalysis and nanomaterial, and the properties of nanomaterial and the properties of photocatalysis, how one can use in the field of wastewater treatment. Then I'll take some specific example like oxide nanosemiconductors for the degradation of azode dyes. Actually, basically, azode dyes are coming from dye industries. So I'll give more details about dye industry, why we need to worry about dye industry in the present context. Okay. And then the fifth one, which I'm going to take, oxide nano semiconductors for agricultural waste degradation, specifically from pesticides. Because in the day-to-day life, many farmers people are using these pesticides for growing plants. So, but ultimately, we are dumping all these pesticides on the ground. Okay, so we have to degrade those pesticides for the effective utilization of land for the futures. Okay, then the last application which I'm going to use, sunscreen, for how to use sunscreen, and what is the current trend, and what we have done for the fabrication of sunscreen in the real time application. So that was, this was my outline of my talk is going to be. Before I enter into my talk, actually, I just give the glimpse of my research group. Actually, my research group is mainly focused on three different areas. First one is renewable energy production, like solar cell, hydrogen fuel production, transfer and conducting electrode material. And then second one is related to environmental applications, that is related to photocatalysis and wastewater treatment, like that we are doing. And some of our students are working on this biomedical application, like antimicrobial, anti-cancerous studies, and sunscreen applications. So these are the uh, area which we are doing in our laboratory at IIITDM-Kurnool. Okay, so now we'll go to the first topic, which is related to wastewater treatment. Why wastewater is necessary? Wastewater treatment is necessary, right? So if you look at in India specifically, the wastewater generation in India, there are two main sources of water contaminations. One is mainly due to sewage, other one is industrial waste. Okay, if you look at the data, you'll be surprised because how much sewage wastes are generated in a day in India. Actually, India generates sewage of almost 72,000 million liters per day. We can imagine how much amount of sewage we are generating. Okay, so out of this roughly 72 million liters per day, almost 60 percentage of sewage waters are not treated. Only 40 percentage sewage wastes are treated, and we are reusable. And remaining 60 percentage of the sewage water is untreated, and directly we are just disposed into rivers, lakes, or groundwater. Okay, so with the increase of our population, from if you look at pre-independence and after independence, now our population is almost 1.3 billion. So with the increase of population and industrial landscape is increased and exponentially, that wastewater accumulation of wastewater also it is going to be increased in that particular scale, like the exponential increase of population and industrial expansion, which actually is giving alarming signal to to the concerned authority that we have to treat this waste before you dispose to water bodies like rivers, lakes, or groundwater. Right. In addition to that, if you look at the recent data, the fresh water is actually shrinks. The sources of like rivers, wells, ground, that water is actually reduced. So we have very limited number of resources for fresh water, and we are generating large amount of your waste, right? So you have to ultimately what you have to do, you have to treat the water, and then try to use reuse for the future generation. Actually, these data are actually I took it from Ministry of Environmental, Forest and Climate Change, Government of India. These data are available. Actually, if you look at the data, I have given very few, but if you look at the data, you'll be surprised, and you'll be worried about the nature which you are contaminating. Okay, and I think this data actually I took it from some newspaper, specifically from Andhra newspaper. Day-to-day life, you may see these kind of images in the newspaper, right? So almost many parts of our country is actually contaminated, and some parts even you do not have fresh water, right? And some places there are mainly near to industrial area. The industries are actually we cannot claim all the industry, but majority of industries are actually they are not treated 100%. They just dispose those water contaminated water into the river bodies, right? And specifically, if you look at the data, the Andhrapradesh Pollution Control Board, they have collected a water sample for quality analysis for various rivers in Andhra Pradesh, like Tungabhadra, Godavari, Krishna, Nagavali, Pennar, and at different places they have collected sample. And what they have declared is these places actually the water which we are drinking is not fit for drinking. So actually this was declared by APP control board. Okay, I think this claims I took it from a newspaper. This is some I think 2 years back this news came. It means you can think about the water which we are consuming actually is any one of these river, right? So most of the waters are actually not fit for drinking. So you have to treat properly before you consume, correct? So now I'm going to use a specific case study. I'm going to use textile industry because my topic is I have specified as azodai degradation. So where we are getting azodais majority, okay? Uh, Basically, it comes from the textile industry. Uh, text, anything? Okay. Basically, it comes from the textile industry. And if you look at the data for the textile industry, in the globe or in India, both in global textile market size, it's around 1,000 US dollar, 1,000 billion US dollar in 2021. So that data which we are telling is in 2021, it was the global market textile market size was close to 1,000 US billion dollar, but it is expected to reach 1.99 trillion dollar by 2030. This is the global statistics. What about India? India is one of the largest exporter of textiles in the world. And if you look at the country GDPs, this textile industries contribute 2.3% of country GDP. Also, it's one of the second largest employer in the country, which provide the direct employment to around 45 million people, direct employment, and 100 million people in allied industries. So almost majorities of that is why we are called this textile industries a second largest employer. What about the share textile industry is almost 11.1 billion US dollar is we are export this cotton textile to almost the entire world in 2020, 22 to 23. We are expecting that it will reach 250 billion market size by 2030. It means we are almost, you can think about how much textile, how much dyes are using every day in India in the textile industry. That's why I took this data. This data actually I took it from investindia.go.in. So where you can get what is the recent data. This actually I took it from the last week. I took this data. Um, Okay, so this is the actual picture about the textile industry in India as well as the global. Now we'll come to how much water we consume for the textile industry. Okay, so if you want to fabricate this wool material, minimum you have to have 111 meter cube per ton material. You have to use this much water to make a wool. Minimum of I'm saying. So the maximum amount it can go to up to 659 meter cube per ton. Similarly, if you want to fabricate a carpet, it will take 8.3 meter cube per ton, and maximum it will go to 163. Okay, so this much water we are consuming, and the dyes which we are using is mostly like acid dyes, reactive dyes, azo dyes. Depend on the material which we are going to fabricate. These different dyes are used. For example, if you want to make a wool or nylon, you have to use acid dyes or reactive dyes for wool. And for cotton and viscose, day-to-day, if you are using cotton material in our comfort, for that we are in the dye industries are actually are in the textile industries are using azo dyes. Basically, it's azo dyes. But what is the problem? So people are using. What is the problem of using these dyes? Actually, if you look at the data, if I use some 100% of dye to make a wool material or nylon material, out of 100, almost a minimum of 7 to 20% dyes are not going to fix on the material. Okay, so these unfixed dyes are actually it's mixed with water, and if this water is not treated properly, then these dyes are actually you are going to dispose into water body or river, water body in the sense river or pond or sea or ocean, wherever it's possible. These dyes are actually now you are going to mix with the fresh water. Okay, so what will happen if you mix this unfixed dye into water? The typical characteristics of this untreated textile effluent, the pH value of this untreated dyes will have value of 6 to 10 pH. Temperature can go up to 45 degree, and this biological oxygen demand or chemical oxygen demand will vary, and it is a huge number. And similarly for total suspended solids, it will vary from 15 to 8,000. Total dissolved solids, it can vary from 8,000 to 12,000. And the chlorine level, sodium level, it is increased. In addition to this the chemical parameters, there are trace amount of elements are possible in the acidic. That is iron, zinc, and more specifically like arsenic, mercury. These two elements are actually highly dangerous. If these waters are untreated, if we consume or any other living organism consume this particular element, actually it will create a lot of problems to our body. Okay, so what are the problems which you encounter if you consume this untreated textile waters? Okay, there are many derivatives or aromatic amines are available in sodides, like 1-naphthalamine, 2-naphthalamine, and there are several aromatic groups are available. Okay, so if any one of these groups, suppose if 1-naphthalamine, if it is not treated and you are consuming, and then this actually it is going to create a problem with your body. This is a degree of human carcinogenity. This will give slight effect, but if you consume 2-naphthalamine, it will create severe effect. Okay, so in some case it will be severe. So these are the things which we are going to encounter in our day-to-day life. If you are living in that particular area, in the industrial area, these water bodies are actually highly contaminated. Okay, one specific data was collected from Tamil Nadu, uh, and specifically from this district, Tirupur district. Because this Tirupur district is mainly focused on dye industry, textile industry. Actually, one of the largest exporter in India is Tirupur. Okay, so there they have this Center for Science and Environment. They have analyzed the data, and they have classified five classes of water: class A, B, C, D, and E. Where class A is a drinking water without any treatment. Just you can do some disinfection, like you just boil the water and then you can drink. That is called class A water. Class B means just a bathing water, outdoor bathing water. Class C is drinking water, but you have to do some conventional treatment followed by disinfection. And for class D is basically it's fish culture and wildlife propagation, like a pond or river or something. Class E is related to irrigation, industrial cooling, or controlled waste disposal. So these are the classes they have classified in that particular region. In Tirupur district, they have collected almost some 15 different places, and they have analyzed different. They have collected data from pond, river, and different lakes, dams, and they have classified based on this class A, B, C, D, E, and they have analyzed each parameters like pH, total dissolved solids, total suspended solids, COD, chlorine level, different compounds like sulfate. These are the properties that they have evaluated in different places. Suppose if you if you want to say that your water is class A water, then the pH level should be 6.5 to 8.5, and the total dissolved solid should be maximum 500 parts per million, and the chloride level can be up to 250 parts per million, and your sulfate compound should be 400 parts per million, and other compounds like sulfides, COD, TSS, TS should not be there. Okay, if it is class B, then your pH level can up to 8.5, 6.5 to 8.5. Then there should not be any TDS, there should not be chlorine, there should not be sulfate or sulfides. Okay, similarly, they have classified all other three categories. What they have found is, for example, if you take the first one, Samalabrom pond, their pH is almost 7.2, that is fine. But the total dissolved solid, that is 1200, right? Whereas class A is it should be around 500. If it is class C, it is 1500. Class E is 2100. But this here it is 1200. If you go to some other place, it is that range is actually almost 5 times greater than the allowed values, right? And also the other values like TS, TSS, COD, this is actually is a huge number, right? And what they have given at the end, these waters are actually not usable directly, whether it's a drinking water or it's going for a fish culture or wildlife propagation or irrigation purpose, industrial cooling or even controlled waste disposal. These waters are not useful. Okay, so these are the typical problem which we are encountering in our day-to-day life. Even we are come across all these industries nearby or close to our living places. We are living in this particular environment. So we have to treat the wastewater before you consume. Okay, so what are the, so now it is a second topic, that is what are the various technology or treatment which is available for the dye degradation or textile effluent degradation. Okay, there are three different way we can classify. One is a conventional method, the other one is a established recovery method, the third one is emerging removal method. Okay, the conventional method is related to like a coagulation, precipitation, biodegradation, filtration, adsorption. So these are the methods which are available, but the problem with this conventional method, at the end of your wastewater treatment, you will end up with something like a sludge. Okay, so you will generate a lot of waste out of your conventional method. So how then the problem will come how to convert these accumulated sludge into usable material. That is another problem we'll encounter when you go for conventional method. And the second method is established recovery like evaporation, oxidation, electrochemical treatment, membrane separation, membrane bioreactors. These are available for established recovery. Somehow it is compared to conventional method, this is a better method. But still, there are some problem you'll encounter. Suppose if you take some azo dyes and you are trying to do this established recovery method, and if the reaction is stopped in between, okay, in between, or if the reaction is incomplete, then what you will encounter is that intermediate product will be much more toxic than your parent material. Okay, so even after treatment, our purpose is to treat this wastewater to make sure that the water is usable. But at the end, what you are going to do, you are end up with something like intermediate product. Those intermediate product is actually is not going to be useful. That will be more harmful than your uh, parent material, untreated water. Okay, there are, but still we cannot say that 100% there will be a unreacted product, but there will be a advantage as well as disadvantage. Advantage. And the third method, which is emerging removal method, there we have advanced oxidation process, nanofiltration, biomass, bioabsorption, adjustment onto non-conventional solids. These are the emerging removal method which are available in the recent years. But in this, among these several available method, I'm going to focus advanced oxidation process method, where you have a lot of advantages, okay, compared to other method. Like even if you go for a nanofiltration method, there you will encounter a problem with the sludge. You will at the end you will get some amount of sludge, which is a byproduct of that. So you have to convert those sludge into a usable product. So in order to avoid that, um, we are going for advanced oxidation process. So advantage of, what is the advantage of advanced oxidation process? Okay, so this advanced oxidation process nowadays the most common approaches for water or wastewater, groundwater is something like this. You can classify into 5 categories: sorbents, adsorptions, chemical reaction, photocatalysis, filtration. So for carbons, mainly different nanoparticles are used to deposit all this waste onto nanoparticle, and then you remove waste from the water. And similarly for adsorbents, people used various nanoparticles, carbon is carbon nanomaterials. And when chemical reaction, like we use different kinds of nanoparticle to reduce those harmful uh, chemicals to usable chemicals. And photocatalysis actually is more or less similar. Here we have to use catalytic material plus available photons, light energy, to uh, to dispose or to decompose uh, your parent material or harmful chemicals into usable chemicals. Okay, and similarly for filtration, that is we are talking about nanofiltration. There we can use different kinds of nanocomposite carbon material. Even for carbon material like graphene oxide or graphene material as a ultra thin film filter to remove cadmium or mercury, arsenic. Those harmful elements can be removed using filtration method. Now in the whole of my lecture is going to be advanced oxidation process. So what is the advantage of this advanced oxidation process? So here advanced oxidation process is typically is entirely different from conventional process. It will what the advantage is actually this advanced oxidation process will decompose your organic compound in the water is completely degraded into carbon dioxide or water or different mineral acid. I see. Rather than the concentrated or transferred into different places. Like as I said earlier, in some cases you may get some sludge, but in this case you are not going to get any sludge, and you are not going to get any intermediate also. So if you do a reaction for a period of time, you will end up with useful product like a carbon dioxide or water or different minerals that you will get it as a end product. So this is entirely different from your conventional method, because conventional method is normally you will end up with something like a secondary waste as a sludge. But here you are not going to get it as a secondary waste. It will be completely converted to carbon dioxide or water. Okay. The main key ingredient for this advanced oxidation process, that is called hydroxyl radical. This radical species that will attack your dyes or organic compound, then that organic compound will break into different molecules. Finally, you will end up with carbon dioxide and water. Okay, so you take the organic pollutant like azo dyes, you send this hydroxyl radical, make an intermediate, and then again you pass this hydroxyl radical, attack this intermediate product, then convert them into carbon dioxide, water, and different various minerals depending upon the source which you are taking. Okay, so in advanced oxidation process also you can classify into two different broad categories, that is a homogeneous process, heterogeneous process. In homogeneous process also you can classify into two different way: photochemical, chemical. Heterogeneous also you can take it like chemical and photochemical. In photochemical, as the word suggests, it is photon and chemical process, right? So we need light energy. So basically we'll take a photon like a UV photon, and then you can use a different ultrasound, ozone, hydrogen peroxide, the combination of these three. Then this comes under category of photochemical. Basically you need photons. But the other one is a chemical method where you don't need photons. You can use ultrasound, different electrochemical oxidation process that comes under chemical method. Okay, so in what we are going to use, a photochemical method where I'm going to use this ultrasound, that is sonolysis and photolysis with some catalytic material which we are going to use as a titanium dioxide or zinc oxide as a catalytic material. Okay. So what is now the third part is the introduction to photocatalysis and nanomaterials, right? So what is the meaning of photocatalysis? Is there any photocatalytic process available in nature? Yes, if you look at the in nature, our these plants are actually making photocatalysis process very effectively. That is called we used to study as a photosynthesis process. If you remember your school level physics, they used to give this particular picture where your plants having this chlorophyll compound which harvest this sunlight, the energy from sun, and use your water and carbon dioxide which are available in the environment, convert this carbon dioxide from the air, and it convert this particular carbon dioxide into chemical fuel, that is sugar. But the problem is the process which plants are taking, the efficiency of this particular process is almost close to 1%. Okay, so if you want to mimic this particular natural photosynthesis process, the efficiency is very low. So you have to increase that activity to some level so that the percentage of your efficiency will go high. That is why we are going to use catalytic material to boost that reaction, right? So naturally there is a possibility, but we want to make it like a speed reaction. We want to increase the speed so that you can produce in a large quantity. So for that you need some catalytic material. So that catalyst means it will increase that um, reaction. The catalysis means increase the reaction, right? So this in this case, what we are going to use is the semiconductor catalytic material, which is photosensitive. Okay, so if you use this catalytic material, what artificial photosynthesis does is, here we take sunlight using the catalytic material, semiconductor catalytic material, take the water, split into water and oxygen. Right. That is why people are using nowadays this catalytic material used for hydrogen production. Right. Hydrogen production is basically it's a catalytic material only. Okay. It is actually mimic of your natural photosynthesis process. But there is a problem because the photosynthesis process, what it is, plants are taking energy from sun and harvest carbon dioxide and water from the environment and convert them as a sugar and oxygen. That is why we are getting oxygen from the plants. But this is not the instantaneous process. It's actually something like a hill. So if you want to overcome this hill, you need some chemical energy. In a similar way, if you want to do artificial photosynthesis process, if you want to split water into hydrogen and the oxygen, you need this much amount of chemical energy, that is a Gibbs free energy, 237 kilojoule per mole. It's almost 1.23 electron volt energy. That is why this is not instantaneous process. Even though we have a lot of water and we have a lot of sunlight, water is not going to split into hydrogen and oxygen, right? Because it has to go through this particular uphill process to make this reaction possible. That is water to hydrogen and oxygen. Okay, so this is a typical process of photosynthesis. And I think it was given in Japan, one center, photocatalysis International Research Center in Japan, that they have given some vision of feature community which is purely based on photocatalysis. Okay, so why? Because if you use photocatalytic material, you are going to have pollution-free environment. Okay, because you are going to produce hydrogen from solar. So if you use hydrogen, there is no emission of carbon. So by the way, you can reduce this carbon accumulation in the air, and then you are going to, once you reduce this fossil fuel consumption, then usage of hydrogen fuel, then almost entire problem related to atmosphere will be solved, right? And if you use your photocatalytic material for the degradation of your wastewater from the industry, those things can be resolved. So this was a proposal which they have given as a vision for future community purely based on the photocatalytic material. Okay, so this you can check this website. You can see that update of how they are going to implement in this particular aspect. Okay. As I said, we are going to talk about the photocatalysis. So we need to know um, what photon we want to use, what is the restriction of utilization of your photons. Okay. So if you look at your electromagnetic radiation, yes, electromagnetic radiations are actually it span from high wavelength to very short wavelength. Start from radio wave to gamma rays. In between, you are getting visible light, which is making wavelength range of 400 to 700 nanometer. Okay, roughly around 400 to 700 nanometer. Uh, Actually, other radiations are not usable because since you are taking the semiconductor has band gap of around 1 point, around 1 electron volt to around 3.5 electron volt, which is roughly around this visible light, UV to visible light. So beyond, if you use infrared or microwave, radio wave, or ultraviolet, X-rays or gamma rays, those radiations are not useful. So we are going to restrict our discussion only between ultraviolet to visible light. Okay, so roughly around 195 nanometer to 700 nanometer range. That energy only we are going to use it for your photocatalytic material. Okay, and we are going to combine this photocatalysis with sonolysis because ultrasound, which we are, ultrasound if you use, it has some property to make hydroxyl radical. Because as I said in the previous slide, one of the important key ingredient for the photocatalytic process is production of hydroxyl radical. So if you use sonolysis process, there is a possibility of production of high hydroxyl radical. Okay, so what is ultrasonic wave? Ultrasonic wave is something like a compression and expansion, right? So that is ultrasound wave. So if you send this ultrasound wave into liquids, okay, so what will happen? This will create a kind of bubble. In the beginning, there will be a bubble formation, and over a period of time, in the period of time, in the sense it is around microseconds, these bubbles will start to increase. The size of your bubble start to increase. Once it reaches that particular uh, size, around micrometer size, this will start to collapse. Okay, so here you have acoustic pressure, that is a compression and expansion, and if you send this wave into water, this bubble radius will try to increase, and then once it reaches the critical size, it start to explode. Okay, so this very short time explosion, it creates kind of hot spot. So if you check the temperature and the pressure, it will be amazing because the temperature in that particular scale, micrometer scale and micrometer radius, in the microsecond time scale, it produces 5,000 Kelvin temperature and 2,000 atmospheric pressure in that particular volume. Okay, so this much high energy, production of high energy, that will lead to breaking of this water molecule into radical like a hydroxyl radical and OH radical, and then ultimately you will end up with production of OH radical and the formation of hydrogen peroxide. So what we need is we need a hydroxyl radical, right? So here in the if you apply this sonolysis process, ultrasound in the water, you will produce OH radical. Okay, so this OH radical will try to attack your dye molecule, and that dye molecule will degrade into different usable chemical like carbon dioxide or water or any other minerals with the usage of sonolysis. So what we are going to use, we will use this photocatalytic material as well as this sonolysis process, that is called sono-photocatalytic process. So these three processes, if you combine, the efficiency of degradation will go high in comparison with the respective process like sonolysis, photolysis, or catalysis. Okay. Now you may ask question, why semiconductor is useful? Can I use conductors? Can I use insulator? The answer is actually the photocatalytic material is there is a process called band gap. Okay, because you need to harvest the energy. Like your plants are harvesting energy by use of chlorophyll, right? So the chlorophyll, that compound will harvest the energy. So in order to harvest the energy, you need some band gap. If you use your what you call conductors, there is no band gap, so there is no energy absorption. So what will happen if when the energy falls on the material, the electron just to conduct, the conductivity start to. But we don't need that process. We need to harvest that energy, so we need some band gap, right? And the metal should have a highly crystalline material. If it is amorphous material, then that properties of photocatalysis will vary. And we need highly surface area to absorb all these dye molecules on the surface, and it should be chemically stable. Okay. And if you look at the solar energy spectrum, at the sea level. This is a typical solar spectrum. And this spectrum, if you look at the solar irradiance, that is watt per meter square per nanometer, and most of the energies are actually the high intensity is around 300 to 750 nanometer. If you look at that, that is actually in the visible range, right? So if you want to harvest the visible light photon from the sunlight, then your band gap should match within this particular range, right? So if you have band gap above this or below this, you will actually lose this particular visible light photon, right? You will suppose if your band gap is very low, then you are reaching almost this particular range around 1100 or 1000 or 1200 range. Then you are losing your solar energy photon, right? So you have to avoid that particular case scenario. So your band gap, actually the semiconductor has a band gap in the visible range. So that is the reason we are using semiconductor. Okay, and and these are the how you define the semiconductor, like bands, right? So if you take just a one atomic orbital, you'll go only one energy level, and if you take two atom, that is molecule, the energy level will split into two parts. That is HOMO and LUMO. HOMO is a highly occupied molecular orbit, and LUMO is a lowest unoccupied molecular orbit. And if you take a number of atoms into in, then this energy level is split into many energy levels, right? So if you have large number of atoms, then the energy is actually, this band is actually now the single energy is consists of n number of energy levels. That is why you are calling this as a bands, right? Energy bands. You are calling them as a energy bands. So, but what are the problem is happening actually when you shine the light? Okay, the problem is the moment when you shine the light, the electrons which are available in the valence band will try to capture this energy, and it will make a transition to conduction band if the energy is sufficient. If the energy is matched with this band gap, the electrons which are available in the valence band take up the energy, transform into conduction band. But the lifetime of this electron in the conduction band is very short. It's around a nanosecond. Then after nanosecond, it has to come back to this valence band, right? So then there will be a recombination process, right? But we need to separate this electron and hole pairs. Then only this electron and holes can participate for the reduction and oxidation process, which will convert that azo dyes or any waste organic molecule into usable molecule. But before it reaches this surface of your material, there are different process will happen. That is called volume recombination process, surface recombination process. Suppose if your material is bigger enough, the size of your material is big enough, then the moment when you shine the light, this electron hole pair will generate, but this electron hole pair will immediately recombine, because before it reaches this surface, it will recombine because the size is bigger. It will recombine and it will annihilate. That we need to avoid, because we need to separate this electron hole pair effectively. In addition to that, there is a possibility of surface recombination, because even after reaching the surface of your material, this electron and hole pair can annihilate and become zero, right? So if you see this, the time scale, this recombination process will take 10 power minus 15 scale, 15 seconds. Okay, recombination process is 10 power minus 9 seconds. So the creation of this electron hole pair is in the 10 power minus 15 seconds. That is 1/5 seconds. Okay, suppose if you can effectively harvest this electron hole pair separately, then the reduction process will happen. That time scale is 10 power minus 3 seconds, whereas the oxidation process will take 10 power minus 8 seconds. Okay, so this reduction and oxidation process will help you for the conversion of your organic molecule into usable chemicals. Now you understand why we need nanomaterial, right? Now your size of particles should be as small as possible, so that your volume recombination process can be avoided, right? And also surface recombination process can be avoided, because the time scale is 10 power minus 3 to 10 power minus 8 seconds. So you have to avoid this surface recombination as well as volume recombination process, so that you can take these electron hole pairs for the reduction and the oxidation process further. So you need size of your particles should be much smaller. So to get that size, appropriate size, we are going for nanomaterial. Like now we are going to the real world, the advanced nanostructured material for wastewater treatment are the environmental applications. Now I gave justification why we need nanomaterial, right? So now how would you define nanomaterial? Okay, the nanomaterial, if you want to define, it is very simple. If you can define something like this, the motion of electrons are constrained in any one of the dimension, then that material you can call them as a nanomaterial. It can be one dimension or two dimension or three dimension. For example, here I have classified that nanomaterial into three parts. That is a zero dimensional material, one dimensional material, two dimensional material. Zero dimensional material is something like all this motion of electrons are constrained in all three directions. Okay. Whereas one dimensional materials, the motion of electrons are constrained in two directions. Whereas along the length, there is no restriction. The electron can make a movement. Okay, they are free to move. Like a nanowire, nanotubes, those things are comes under one dimensional nanomaterial. And two-dimensional nanomaterials, as the name suggests, along the two directions, the motion of electrons are possible. Only one direction, the electrons are actually constrained to move. Okay, the thin film and graphene sheet, those things are comes under two-dimensional material. And three-dimensional material means all three directions the electron can make a movement. The bulk material which we are day-to-day life you are seeing, those things are actually bulk material. But what is the interesting thing? If you notice, this zero-dimensional material or one-dimensional material or two-dimensional material, the allowed energy levels or the density of states. Actually, if you look at the three-dimensional material, the density of states are actually, it's a continuous. If you go from at Cape on, it is actually continuous energy levels. Whereas if you take a quantum well or the two-dimensional material, these energies are not continuous. It's actually discrete. It's like a step-like function. Step-like function is showing, right? So not all energy levels are allowed. It's only few energy levels are allowed energy levels. That's why you are getting a step-like function. Similarly, if you take a quantum wire, then the function is actually something like a sawtooth, right? It's a sharp function. But if you take it to zero dimensional case, quantum dot, then the energy levels are actually well discrete energy levels. Okay, so not all energy levels are allowed energy level. These properties actually makes a material very efficient for photocatalysis. Not only photocatalysis, for any other optical applications also very useful, highly useful material. Okay, but how do you define this nanomaterial? I think most of the people might have studied particle in a box problem in a quantum mechanics, where particle, if your electron is confined in a small volume, right? Like this is the particle in a typical particle in a box problem, where the electrons are confined in a small volume. Electron cannot make a movement outside this box. If this be the case, if you solve this Schrodinger time independent Schrodinger wave equation, then the energy of this particle is related to n square h square by 8 ml square. It means n is constant, h is constant, m is mass of electron, and n can take value from 1, 2, 3 up to n, up to infinity. Only the variable is length, right? That is the length of the box. So if you change the length of your box, the energy of your energy is actually is vary. Suppose if your length is high, energy is low. If length is low, energy is high. So what you are going to do, if you take n is equal to 1 for the ground state, the energy is corresponding to that energy is En, which is equal to n square h square by 8m. That if you take L as a 10 nanometer or a 5 nanometer scale, then energy will be one particular thing. Then n is equal to 2, n is equal to 3. So you are going to get discrete energy level rather than continuous energy level, right? Now, how you model your particle in a box problem to nanomaterial. So this particle, this box as a model as your particle. So size of your particle, if you reduce into nanometer scale, the reduce into size of your box, then the electron which are available in this particle will confine within this particle. It cannot come out from the particle. So you can model this particular nanoparticle as a particle in a box problem, so that this energy of electron in the nanomaterial is equal approximately equivalent to your particle in a box. Suppose if you want to tune your band gap of your material, in the traditional way it is not possible because you want to find alternative material to tune the band gap. But here there is a possibility because just by changing the size of your particle, because L is your size of your particle, just by changing the size of your particle, this energy will increase. Suppose if you reduce this size of the particle, the band gap is increased. If you increase the particle size, the band gap is reduced. So depending upon the size of your particle, the band gap can be tuned, right? As I said the earlier, we need to harvest your solar photon in the visible range. So how to make it? Because you have to tune your band gap to this particular value, right? So in the conventional way, it is not possible because the band gap is fixed. Whereas if you go to nanomaterial, with respect to size, one can tune the band gap. That is one advantage of having nanostructured material. Okay, and widely used nanostructured material for photocatalysis or wastewater treatment is titanium dioxide because it has a vast application in the field of water purification, agriculture, medical, printing, electrical applications, air purification. So, almost entire range of applications are available with respect to titanium dioxide. Also, zinc oxide also used. In our discussion, we are going to concentrate to titanium dioxide and zinc oxide. Okay. So the first example which I am going to take, as we have used gold doped titanium dioxide. Okay, gold and nitrogen doped titanium dioxide known as PS for the degradation of diazo and triazo dyes with the help of sunlight. Okay, so if you look at this particle, this is the typical transmission electron microscope image of titanium dioxide nanospheres. And with a high resolution transmission electron microscope, we have identified the presence of gold particle on top of your titanium dioxide. And used, we have prepared this material using a solvothermal method and use this material for the degradation of your diazo and triazo dyes. So what we have done is we have taken this prepared gold nitrogen doped titanium dioxide nanosphere with amount of 0.2 gram per liter, and the dyes are fixed around 4 into 10 power minus 5 molarity. Okay, and we have used two different dyes. One is RR120, that is reactive red 120, and the direct blue 71. Okay, these are the dyes are actually these are directly coming from the textile industry. There is a diazo and a triazo, and we have used sunlight uh, to analyze this effective degradation of this diazo and triazo dyes. And if you look at the data, this black color, that is just we have used only solar light without use of any nanomaterial. Okay, so without use of any nanomaterial, just there is no degradation. Almost the degradation is zero. But after usage of titanium dioxide, this particular curve, that is violet curve, there is just use of titanium dioxide which we purchase directly from the market. Okay, it is not nanomaterial. Okay, that has very low percentage of degradation. And when we use porous titanium dioxide alone without any doping, then it has slightly increased efficiency. But when I add this nitrogen as a dopant, it is increased further. When I use gold nanoparticle doped titanium dioxide, it is increased further. But when I combine these two, titanium dioxide along with gold and the nitrogen, the degradation process is uh, highly efficient. Okay, highly efficient process. Okay, then we varied with two different dyes, and we have verified, and it was identified that for direct sunlight, it has highly usable, and it is directly convert those diazo and triazo into usable chemical like water and carbon dioxide. Okay, but as I said earlier, if you use a titan advanced oxidation process, you should have hydrogen hydroxyl radical OH radical production. Okay, so how to calculate this production of OH radicals? How much amount of OH radicals are formed? Because as I said, if I use only sunlight, there is no degradation. If I use only titanium dioxide, which are commercially available, then the degradation is very small. And when I use a different combination of material, the degradation is fast. Why it is more? Degradation is more for this kind of material. That we have to analyze how much OH radicals are produced in the each material. Right? In order to get that data, that production of hydroxyl radical, we will use terephthalic acid as a medium that with a concentration of 5 into 10 power minus 4 molarity, and take a PL photoluminescence spectra with no catalysis. That is your black color. That means there is no, without catalysis, there is no production of OH radical. And then with catalysis, without any light, that is your second graph. That is also almost a negligible OH radical production. Okay, so when you use the titanium dioxide, which is commercially available material, then the OH radical formation is started to give, but the amount of OH radicals are very low. Okay, then increase the different kinds of material, and the OH radicals start to increase. But upon light, upon visible light, the OH radicals are increased enormously. That too for almost 100%, not 100%, around 90% of OH radicals are produced in the material porous silver, gold and nitrogen doped titanium dioxide material. Okay, so the OH radicals are highly appreciable in the case of combination of gold and nitrogen doped titanium dioxide. That is why you are getting the degradation is very fast and highly efficient degradation. Okay, and anyway we are going to use in the day-to-day life. So we have verified these dyes, if it is not in the controlled atmosphere like distilled water. If you use ordinary tap water in our home, we have tap water, right? So in the tap water you have a lot of ions, minerals, those things are available in the tap water. If you mix these dyes in the tap water, what will be the percentage of dye degradation using our preferred material? So we have done that analysis, and we have identified that almost 10% of degradation process was reduced compared to the double distilled water or milky water. Okay, that is because in the tap water there is a problem with the chloride ions, because as I said, yeah, right now there are many ions are available in the tap water like chloride, sodium, magnesium, potassium. Those ions are available in the tap water. But the problem is this chloride ions, the presence of chloride ions in the tap water, that will actually act like a radical scavengers. Okay, so that will reduce this production of your OH radicals. Okay, that is why the degradation process was reduced to 10%. 10% of degradation was reduced compared to your milky water. Okay, but anyway, compared to milky water, it is reduced. Even then, still our material can degrade our azo dyes and diazo dyes and triazo dyes effectively, and convert them into uh, water and carbon dioxide. So this is one example which we have model as a degradation process using titanium dioxide. Okay, and the second one, which is related to agriculture waste, simazine. Simazine is actually 2-chloro-4,6 by ethyl amino acid triazine. Actually, this is kind of a pesticides, synthetic pesticides, mainly used to this related to herbicides group chemicals, which are used to manipulate or controlled undesirable vegetation, because many farmers use cultivate some particular vegetables, but suppose in some other plants are growing, that plants are actually it's attack our needed vegetables, then we have to remove those plants. In order to remove that, these particular synthetic pesticides are highly used. But the problem is maximum solubility level of this simazine is 5 milligram per liter. Okay, and the excess amount of this, if the farmers are used more than this 5 milligram per liter, those amounts are actually not going to be soluble in the water. So those excess simazine pesticide will be discharged into the uh, land during rainy season or running water. Okay, so because of this highly insoluble pesticide, it will accumulate over a period of time. That will actually contaminate the land. So you cannot use effectively for the further process. To avoid this problem, you have to um, you have to degrade this particular pesticides into water or carbon dioxide so that you can use that land for future process. So for this process, what we have done is we have prepared this gold and titanium dioxide material, and high resolution term confirm that the presence of gold and titanium dioxide in this case. And here we have used this simazine, the maximum solubility level, that is 5 milligram per liter, and cold doped titanium dioxide, that is 1.5 gram per liter. Okay, and we have applied a different process like photolysis. It means only applied sunlight, and sonolysis means only application of ultrasound. Photocatalysis means application of photons plus catalytic material, that is gold doped titanium dioxide. Sonocatalysis means without light with application of ultrasound plus catalytic material, and sonophotoCatalytic material means application of ultrasound, photons plus catalytic material. And if you look at the data over the period of time, this up to 8 hours, around 7 hours, it's completely converted, simazine converted into water and carbon dioxide. If you use only photolysis, the degradation process is very small, almost only 10% achieved. And if you use only sonolysis, even though hydroxyl radicals are produced, but the efficiency is very low. When you compare all other process, the combination of sonolysis, photolysis, and catalysis process, it gives almost 80% of degradation process around 7 hours. Okay, and the degradation process was analyzed using electrospray ionization mass spectrometer. That intermediate product, what are the product was achieved, and what is the end product after 7 hours. It was confirmed through this electrospray ionization mass spectrometry, and it was confirmed that the unprocessed simazine has this particular compound structure, and after you apply this sonophotoCatalytic process, it convert them into carbon dioxide and water and ammonia. Okay, so these are the product which is highly useful for our day-to-day life, right? So by this work, we have what we have done is we have took this synthetic pesticides, completely convert them into carbon dioxide and water. Okay, this is second example. The third example, instead of titanium dioxide, we have used submarine doped zinc oxide nanostructure to degrade this azo dyes. Okay, so we have done this azo dyes with different kinds of synthesized um, zinc oxide, submarine doped zinc oxide with respect to different amount of doping, submarine doping, and it was identified that it is effectively degrade that azo dyes. Okay, finally convert them into acid blue azo dyes, which we have taken as acid blue 113 dyes. Those dyes are actually convert them into water and carbon dioxide. Okay, similarly, we have used another semiconductor like a copper oxide with a different morphology, like rod kind of morphology, particle kind of morphology, sheet-like morphology. These different morphology with respect to different morphology, we have analyzed um, uh, what is the efficiency of degradation process for methylene blue dyes, and we have identified that methylene blue with the different morphologies giving best result. And we have conducted the study of recycling process because this catalytic material should be used for many cycles. Just if you use just one cycle, then again you have to prepare So in order to avoid that, recycling property is one of the important parameter for any photocatalytic material, which will give the stability of your material against your against your dyes. So we have conducted this experiment and we have found that even after 3 cycles, the efficiency is not reduced much. Only 5% of efficiency was reduced after third cycle. So we have continued up to 5 cycles, even we got a 10% reduction. Okay, so it's a highly stable material for a dye degradation process. The last application, maybe in 10 minutes, I'll complete this talk. The last application, that is a sunscreen application. Okay, but in India, mostly we may not use a sunscreen. But if you look at the other parts of the world, whenever there is a summer, they try to apply sunscreen for the protection of our skin from the sunlight, especially for ultraviolet. Okay, why ultraviolet is very important? Why ultraviolet is very important in the present context? Because ultraviolet, actually, if you look at the wavelength, it has actually ultraviolet has three different wavelengths. One is ultraviolet A, ultraviolet B, ultraviolet C, and ultraviolet A is a longer wavelength, ultraviolet B is a medium wavelength, ultraviolet C is a short wavelength. And the wavelength range from ultraviolet C is 100 to 280 nanometer, ultraviolet B 280 to 350 nanometer, ultraviolet A 315 to 400 nanometer. If you look at the interaction of this ultraviolet on our skin, okay, so this ultraviolet C is actually it will captured by this ozone layer. Anyway, even though it is harmful, it is captured by ozone layer. Okay, so there is no problem with the ultraviolet C, but the problem with the ultraviolet B and ultraviolet A. So ultraviolet B, this ultraviolet B rays can enter into our skin deeper on the surface of your skin. It can create some kind of patches, wrinkle, loose skin, premature aging. So this is not that much problem. Sometimes it may take you to DNA damage also, ultraviolet B. Okay, and the ultraviolet A, it can pass through your skin and it can produce this kind of problem like epidermis, dermis, hypodermis. This problem will come into picture. And if you look at your data, maybe you can check it your mobile. What is the UV index in your present area? Okay, in your location. If your UV index is 2, then you are in safer zone. If your UV index is even up to 5, it's fine. But if you go beyond UV index 5, then you are in the dangerous zone. If you are in 11 plus, then it's highly dangerous. It means if you expose your skin on this UV index of above 11, then you continuously for 5 minutes, you are entering into the problem of your skin cancer. Okay, so data shows the malignant skin melanoma in India. Almost globally, 2 to 3 million people are reported as a non-melanoma skin cancer, and almost 1.3 million melanoma cancer occurs every year across the globe. Okay, so annually, if you look at the data, almost 13.2 people are died out of 1 lakh people just because of this skin melanoma cancer. Okay, so that is why people are highly used to this sunscreen product to effectively protect the skin from the UV light. Okay, but if you look at the data in the market, it is available. Even if you go to supermarket, you can get the different kinds of sunscreen product. We have analyzed the different company product like Avenue, Grown Laboratories, different company we have analyzed. The active ingredient which they have taken is zinc oxide and titanium dioxide, and different concentration they have used. But if you look at the band gap of this material, it is around actually UVA 315 to 400 nanometer. So most of the time, if you use this sunscreen, you will completely protect about UVA and partially UVB. You may not completely protect UVB. Okay. So what we have done is we have taken this particular case, how to protect your skin in the entire range of UVA to UVB. For that, what we have done, instead of titanium dioxide, we have used cerium oxide. in combination with the zinc oxide. Okay, so as a core shell material. So zinc oxide as a core and cerium oxide as a shell. Okay, like here in this particular part, this light color, that is zinc. On top of it, cerium oxide is coated on that, and we have varied this shell and thickness of core and shell thickness. Like the beginning, we have fabricated this core, that is zinc oxide as 55 nanometer and shell thickness of 55 nanometer, and then we varied shell and thickness. Like you keep shell thickness as a constant and core as a varied thickness, and shell thickness half of it, like 55 to 25, and core thickness you double that, 95 nanometer, and various combination we have analyzed. Also, we have done with, instead of rod, you take it like a spherical particle, and then with respect to different shell thickness and the different core thickness, we have varied, and we have used this zinc oxide and the cerium oxide as a sunscreen product. Okay, why we have used? Because if you look at the absorption spectra, it has absorption range from around 250 to 400 nanometer, right? So this is exactly match with your requirement of capturing this ultraviolet B to ultraviolet J, right? So that is why we have used this zinc oxide and cerium oxide as a core shell material for effective utilization of sunscreen product. So using this core shell material, we have prepared a sunscreen based on this US Department of Health and Human Service, Food and Drug Administration, Center for Drug and Drug Evaluation and Research, CDR. They have given some approved concentration for the production of sunscreen, and the maximum approved concentration for zinc oxide and titanium oxide is 25%, and remaining chemicals we have got. So based on this particular conditions, we have prepared sunscreen, and we have evaluated the sun production factor, SPF. It's called SPF, and we have found that 24% SPF of achieved for 8% of prepared material. If I increase that 8% to 15%, then that solar production factor is increased to 34%. Okay. Basically, if you look at the data, something like in the supermarket, when you see that UV sunscreen cream, they used to specify this SPF 50, SPF 30, SPF 50. It means, what does it mean? Next time when you go to market, you see that sunscreen product, you will see SPF 50. It means it will protect 98% of ultraviolet B rays. Okay. If you buy SPF 30, it means it will protect 97% of UVB. Only 3% of UVB rays will enter into our skin. Okay. In our case, we are almost achieved SPF 30% for the percentage of 15%. But anyway, approved percentage is up to 25%. We are increased to 25%, and we have reached almost SPF 50. Okay. So the fabricated material is effective utilization of production of UVA and UVB. Okay, so our material can give complete protection about UVA and ultraviolet B rays. And this work was actually, we have collaborated with Professor Carlos from Department of Pharmacy, University of Concepcion, Chile. They have given this, they have fabricated this sunscreen with our material, and they have analyzed this efficiency of solar production factor in real time, and they have given that value is 24, SPF 24 and 34. Okay, I think with that I'll stop now. If you have any questions, just let me know. I'll happy to answer that.
Sir, no questions, sir. Participate, there is no asking the questions.
Okay.
It's vote of thanks by engineering madam, sir.
Good afternoon, sir. On behalf of HNBS department, today I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Dr. Pandiyarajan Garu, for accepting our request and for giving such a wonderful presentation on advanced nanostructured materials for environmental application. and making event meaningful and interesting. Thank you so much, sir. And I would like to express our profound gratitude to our principal, Dr. Suraya ma'am, for her constant support and encouragement throughout the program. Thank you so much, ma'am. And I would like to extend my heartfelt thanks to our beloved correspondent, Srimati V.K. Padmavatama madam, for her support. Thank you so much, ma'am. And I would like to extend my heartfelt gratitude to Srimati V.K. Srivani ma'am, who has initiated us to do this program and continuous support right from his inception. Thank you so much, ma'am. And I would like to express my gratitude to our Managing Director, Sri Raghunath Reddy sir, for his continuous support and guidance. Thank you so much, sir. And my heartfelt thanks to our convener, Dr. G. Haripriya ma'am, and her entire team, and co-convener of this FDP, Mr. Shivaya sir, Jansi Rani ma'am, Jay Prakash sir, Suman Gopinath ma'am, for their continuous support in making this FDP successful. And a big thank to Noor sir and Nagendra sir, who are backbone of this online session by providing technical support. Thank you so much for both of you, sir. And finally, the end of the session, I would like to thank all the participants of this FDP for their glorious presence. Thank you, one and all.
Thank you, ma'am. Thank you.
Thank you, sir.
Thank you.